billions of galaxies. In each of these, there are billions of stars. But in one galaxy, in one small pocket of the universe, there's just one seemingly regular star, and beside it, there lies an entire world, our world. But how does this whole universe affect us? Well, everything on Earth, from the people who live here to the air we breathe, is all here because of the sun. Even though the sun is just like any other star in the universe, it is the center of our solar system, the source of heat and light for our world, and the being responsible for everything on our planet. Still, how does this star provide all of the heat and energy for our world for millions of years? The answer to this question lies in the core of the sun, where hydrogen molecules come together in a process known as nuclear fusion to form helium. Essentially, the particles come together with such force that they actually bond together, with the two hydrogen nuclei forming one helium molecule after a series of chain reactions. This produces an enormous amount of energy, which is projected from the sun in the form of photons, or light. This energy warms the Earth, and it is from this delicate source that our planet was able to sustain life. However, the light the sun gives off isn't only the type we can see. Our color spectrum consists of the colors from red to violet. These colors are only the way our eyes process certain wavelengths of lights, and there is a range beyond that we can see. One form of light that is of a higher frequency than visible color is called ultraviolet because it has shorter wavelengths than violet.
But what exactly happens when UV rays enter our atmosphere? Are they harmful or are they safe? As the UV light enters our atmosphere, the oxygen and nitrogen in our atmosphere absorb half of the more dangerous UVB and UVC rays. Therefore, only UVA and UVB lights enter our atmosphere. Still, these UVA and UVB rays can be harmful to us. The main problem concerned with the sun and its UV light for humans is sunburn. Sunburn is the reddening or inflammation of skin due to overexposure to UV rays of the sun.
To demonstrate the presence of UV radiation on a smaller scale, the first part of our experiment was to simply show how various objects react when exposed to UV light. To accomplish this, we used a black light, which produces UV light and some violet light, as well as various items such as paper money, tonic water, which contains a chemical known as quinine, a glow-in-the-dark wristband, and even a person's fingernails. As you can see, though the tonic water is usually a clear, colorless liquid, under UV light it turns a very bright blue color. This is because the quinine in it is a fluorescent substance, meaning that it absorbs the UV light waves and converts it into a different wavelength or color, which it then gives off in the form of visible light. The next object, paper money, has some symbols that are made from fluorescent material. This is hard to duplicate, so it can be used to check whether or not a bill is counterfeited. As you can see, each bill has very clear markings, which is also why black lights are used as money detectors. Our next object is actually the fingernails of a regular person. Though not as clear as the other objects, many substances from a human being are also fluorescent, such as fingernails, teeth, or sweat. This next object, the glow-in-the-dark wristband, is a bit unique. It is called a phosphor because it can give off radiated light after being charged or energized. The wristband absorbs energy from the sun throughout the day so that at night it can glow softly. However, since UV light is more powerful, the wristband is immediately energized and it glows much more brightly, both in and out of the UV light. Now that we have shown the presence of UV light here on Earth, let's go into its effects. Though the sun is essential to human life, the powerful UV rays do have side effects as mentioned before. Therefore, the second part of our experiment was to test the effectiveness of sunscreen at absorbing these UV rays. Though there is a common conception that the higher the SPF of a sunscreen, the better it isn't clear whether or not this is actually true. For this reason, the purpose of our lab today is to determine the relationship between the level of SPF of sunscreen and the amount of UV radiation it absorbs. If SPF is truly an indicator of the effectiveness of sunscreen, then the amount of skin damage it protects against should correlate with the level of SPF, because the higher the SPF, the more UV radiation is absorbed. In this lab, our independent variable was the SPF of the sunscreen, and our dependent variable was the amount of UV radiation that passed through. However, we also had to control several variables, such as the strength of the sunlight and the clouds blocking it, how well the sunscreen was spread, the amount of sunscreen, the consistency of the Glad wrap, the accuracy of the UV meter, and finally the amount of ambient UV rays or reflected UV light. The materials we used were a box of Glad wrap, different sunscreens with different SPF, and a UV meter. First, the control reading was taken using the UV monitor. 3 trials without any sunscreen were recorded. Next, a piece of Glad wrap was ripped and placed on a table. 3 drops of sunscreen were added to the center of the Glad wrap. Then, the Glad wrap was folded in half, and the sunscreen was pressed down, spreading it evenly. This ensured that no sunscreen was lost, such as if it was done with the finger, and also so that the consistency of the sunscreen could be controlled. Then, the sunscreen was allowed to dry for 2 minutes, before the Glad wrap was lifted and pointed at the sun. Then, the UV monitor was placed beneath the Glad wrap, at an angle where the sunscreen was between it and the sunlight. The UV monitor took a reading 3 times, to ensure 3 accurate trials. This was done for each sunscreen. From our data, we can see that there is a clear linear progression as the level of SPF increases. Therefore, we can conclude that the stronger the SPF of the sunscreen, the weaker the UV radiation, from about 80 milliwatts per meter squared to 15 milliwatts per meter squared with SPF 130.